Today we're going to talk about an important issue when we're planning a test, a modal test, and that is how do we support or how do we hold up the part that we're going to test. So usually the goal of our modal test is to update some kind of model, usually a finite element model. And so we're taking test data, we have a model, we want the two to match. If we do that, we need to also account for boundary conditions, how the thing is held. And typical real-life structures don't just have fixed boundary conditions. There's some kind of bracket or fixture that has to make a fixed boundary condition. Or similarly, they don't have free boundary conditions. We can't measure the airplane in flight. And even if we did, there's aerodynamic forces holding it up that are boundary conditions. So we'll talk about the different options today. One of the most obvious seeming options is to make a rigid foundation or a fixed interface. But these prove actually really difficult to build in practice, and I'll show you some examples. So suppose that we're interested in testing this satellite, right? And this is eventually going to be mounted down here on a rocket. But for a vibration test, it might be mounted on a fixture, or actually this is actually a base shake test where it's mounted on this plate, which is a part of a shaker, and the plate will move at least in one direction, possibly in more than one direction, to simulate the satellite's ride on the spaceship. So if this was our structure of interest, and we wanted to test it like this, we have to ask, what is the boundary condition, right? The plate looks pretty massive, looks pretty rigid, so we could approximate this as a fixed boundary condition. But as we get to high enough frequency, we'll see that this plate begins to have modes of vibration. And we can't neglect those. And for typical frequencies of interest, that might happen relatively low in frequency. A large shaker table like this might have its first resonance at 200 or maybe 500 hertz. And if that overlaps with the frequencies we're interested in, then we'd need to include the plate as part of our model. You saw this in one of the labs, or homework assignments, formerly a lab, and here we had a wooden frame with some steel reinforcing it, and we were clamping a beam to a wooden frame to approximate a fixed boundary condition. And if you look closely at the measurements, at low frequency things looked pretty good, but if you got to high enough frequency, so this would be first mode, second mode, a missing third mode, fourth mode, you see that there are extra resonances that start to show up. And those extra resonances are modes of the support structure that can show up and contaminate things. The other thing that happens is, due to the stiffness of the boundary not being exactly what we think it is, these frequencies move around. You might go from having the frequencies of a truly fixed cantilever beam to one that's pinned or even free right in the limit. So the frequencies moving around and the extra resonances are both issues. One example of this comes from some work I did. We were measuring the vibration modes of a wind turbine blade, a relatively small wind turbine blade. And the company we were doing this for, they had this fatigue testing frame, beefy steel frame, very heavy, and they could mount the blade in this and they would do fatigue tests. So we mounted the blade here and we're doing our modal test to measure the modes of the blade. As we did this, we looked at the measurements and we saw that mode 6 and mode 7 here both have almost the same shape. There's a little bit of a scale difference, but they really had almost the same shape. And as we dug into that a little more, we saw that what was happening, so they both look like what should be mode 6. The solid lines here show you what mode 6 should have looked like. So we had two copies of a mode. And so this was basically a vibration absorber effect, where a resonance of the blade and a resonance of the support structure combined, and we split the mode into two copies. One where the support structure would move in phase and one where it might move out of phase. So we actually were able to do some post-processing on the measurements and do a Ritz analysis to consolidate those modes and try to estimate the one mode we would have had if we had a perfect foundation. But there's always a little bit of uncertainty now in the frequency, right? If we didn't do anything, rather than having one natural frequency for this mode, we have a range, right? It's somewhere between 45 and 52. Okay, so there's one example. One other example from my actually very first project as an undergrad research assistant. We were testing these carbon fiber tubes, axial vibration of these tubes with a weight on the top and an actuator on the bottom. And we had to mount the actuator to something. Initially we had a huge 1-inch thick steel plate, about 3 or 4 feet diameter, or 3 or 4 feet square, mounted on a concrete block a foot thick. And so that was meant to be really, really rigid and to avoid any problems with resonances of the support structure. But this tube is stiff. Its first axial resonance was 1500 hertz. And so we saw all kinds of modes of that very beefy steel plate show up in the measurements. What we finally did was replace the plate with a solid block or cylinder, 8 by 8 by 8 inch approximately of steel. And there the first axial resonance of that block of steel was then on the order of 2000 hertz or so. And so we were finally able to get a fixed boundary condition in the frequency range of interest. But this is something that we see often, that things that we think of as being stiff and rigid for statics, at high enough frequency, everything becomes flexible. There's just, as frequency goes up, these accelerations, these forces go up, and it's impossible to hold something still if you go to high enough frequency. So what do we do then? Well, the most common approach in modal tests is to try to mimic a free boundary condition, since fixed is so hard. So here's a photo of a ground vibration test of a glider. You can see the actuators, the shakers, probably one on each wing. I can't see if there are some other shakers. But notice what they did is with 2 cranes and bungee cords, they've lifted the airplane off the ground so it's as if it's flying. And the bungee stiffness is supposed to be low to approximate that free boundary condition. Another example, fairly recently, NASA, as part of the Space Launch System, tested the core stage of the new SLS rocket, which is being built. This is an artist rendition, hasn't flown yet. But you can see the core stage here, and there it is hanging for its modal test. And it might not be obvious in the photo, but there's some cables, there's a crane. This is basically being held in a free type condition. So nothing is touching on the sides except for maybe some emergency cables that if it sways too much, things would come into contact. The structure is so large they had to test it outdoors. There wasn't a building big enough to hang it in that was available. So in this case, actually, though, the crane, the mass of the crane, the cables, was still stiff enough that that had to be modeled and included in the computer models for the SLS. So they didn't quite achieve a free boundary condition. But that's the approach they took, rather than trying to make a fixed boundary condition for a structure this massive. Would have been really, really difficult. Okay, so the question that comes up in all of this is, when can we neglect the bungee cords, and when do we actually have to include them in our modeling? And everything I'll talk about, I take from some very nice papers that illustrate this and explain it really well. So we'll use a really simple structure to illustrate this. And we've designed everything to make the numbers come out really easily in the math really clear. So let's suppose we're trying to test this system. This system has two modes. It has a rigid body mode where both masses move in unison, and then it has a bounce mode where the masses move in opposition. And by choosing the stiffness as kt over 2, the natural frequency is just square root of k over m, as we're used to. So let's suppose then that we go and we hang that for a modal test by two bungee cords with stiffnesses ks and damping cs. The nice thing is with this approach, the mode shapes don't change. And we can calculate the natural frequencies. What used to be the rigid body mode now is a elastic mode, but it still has the structure moving rigidly. So we call that the support structure mode, or maybe the rigid body mode. And that mode turns out to have a natural frequency of ks over m. So the stiffness of the support structure divided by the mass. Similarly, if we calculate the elastic mode that we're trying to measure, we see that its natural frequency is changed. Rather than being kt over m, its natural frequency is now kt plus ks. So now we have a way of saying how much error will we have in the measured natural frequency due to the fact that we've supported the structure with two springs ks. Right? So this is the type of analysis that could be done. So we can actually work this out very nicely. So if we call the true natural frequency subscript t, the support structure subscript s, and measured subscript m, we get this really nice, what Karn liked to call the easy to remember formula. The natural frequency that you measure is the true natural frequency squared plus the support structure natural frequency squared, square root of that. So we can easily remember this and do calculations if we want to. If you actually solve for the true natural frequency, you can write this equation where this becomes the error term. And maybe I'll just show you really quickly. We can actually, we can simplify that if we do a Taylor series expansion. And so if we define x to be the natural frequency of the support over the measured natural frequency, and we're hoping that that will be a small number, so that would justify a Taylor series expansion, then we can say that the true natural frequency, which is a function of x, will be the expression for the true natural frequency evaluated at x equals 0 plus the derivative of the frequency with respect to x times delta x, or times the change w at the where delta, when x is equal to 0, the support structure has 0 stiffness, right? Plus we could have higher order terms. So if we do this, we get that the true natural frequency, we take this equation and we evaluate it at 0, at x equals 0, and this part all disappears at 0. So that's just the measured natural frequency. And then if we take the derivative, we would get the measured natural frequency times 1 minus x squared to the 1/2. So if we take a derivative, we'll subtract 1. This will become 1 minus x squared to the negative 1/2 times 1/2. And And then we're going to evaluate that again at x equals 0. So things come out really nicely. What we end up getting is that the true natural frequency is the measured natural frequency plus 1/2 of the measured natural frequency times, now we have our delta x, and so that would be Ws over Wm. All right, oops, and actually we need then to multiply by the derivative of the inside with respect to x. Looks like I forgot a little term in my derivative here. Let me just clean that up. The derivative of so that's the derivative of this function here. The derivative of the inside would take, and we'd multiply that by negative 2x, and let's see, and then anyway, if we plug all that in, we oh, okay, I see what I was doing actually. Actually, to make the math come out cleaner, I would have x be that quantity squared. So this would have just been 1 minus x. That's what I was doing. And okay, and anyway, that eventually gives us this expression that we want. The measured natural frequency over 2 times the support frequency over the measured frequency squared. Oops, and we'll have a negative sign on that due to the negative. We get a -1 that will creep in here due to the derivative of the inside. All right, so anyway, that eventually lets us write this equation here. And the key thing is that the error in the natural frequency, or the difference between the measured and the true, is 1/2 times this ratio of frequencies squared. So if we have our measured natural frequency is 10 times the support natural frequency, then what we will get is only 0.5% error in our natural frequencies. So our typical rule of thumb is that we always want the measured natural frequency to be at least 10 times the support natural frequency, so that we can have what might be an acceptable error in the natural frequency. So this isn't too hard, well, hopefully this isn't too hard to achieve. If we're testing something that has a first mode at 100 Hertz, it can be pretty easy to hang it from bungee cords and get that support structure or support frequency down to 10 Hertz or lower. If we're testing something like the SLS, a huge rocket or an airplane where the modes might be, on the order of 1 Hertz, then this might become pretty difficult. We'd have to have a really large crane so that we have a 10-second period or a 0.1 Hertz frequency of the support structure. All right, so we could do the same thing for damping. The easy to remember formula in this case is just the sum of the zeta omega n's. And notice the square. With frequencies we get a sum of the squares. With damping it's the sum of the terms to the first power. And so this one becomes much more sensitive to the damping of the support structure. This error term, we go only as as the ratio of these two. So in our rule of thumb, this would become 1/10. But the problem is that this damping, a bungee cord might actually have 10 times more damping than, say, a metal beam that we're trying to test. So it can be very easy to actually get pretty large errors in the damping. So this is a challenge and something that we have to be aware of if we're trying to apply this to structures. All of this can be extended to an arbitrary system, to multi-degree of freedom systems. One way to do that is covered well in Ewan's book, where you can take the partial derivative of your eigenvalue equation with respect to some parameter. So that might be the stiffness of a support spring. And you can write these equations that tell you how the natural frequency of the rth mode would change as you change that stiffness. And eventually he derives this equation, which tells you that the change in the rth natural frequency will depend on the frequency. Here we have the mode shape at the point where the spring is attached, and then the stiffness, or the change in stiffness that you get by adding the spring, or the stiffness of that support spring. So this is another formula that can be used in a more general case. And here it's telling us something important. If we have a continuous system, say we had a beam, and we want to support it with springs or bungee cords, the effect will depend on the mode shape. So if this is the first mode shape, if we put the springs out here, we have a lot of motion, notice, out here at the ends of the beam. And so we're going to get a bigger error in the natural frequency. In contrast, if we can put our springs at a node of this mode, maybe right in here, we'll get minimal error. This term would theoretically go to 0, and we get 0 error in the natural frequency. All right, let's go through an example of this using the Ritz series that you've been learning about in class, because this will, I think, help strengthen your understanding of how this applies to continuous systems and allow us to appreciate what's happening there. And also just gives a different perspective on what assumptions go into these types of calculations. So remember, the key assumption with the Ritz series is that the displacement, which might depend on position and time, is a superposition of functions of x and functions of time. So we're basically separating the equation. And usually we have a finite number of those functions. Also remember that that on the right-hand side of the equation, the forcing that comes in is a product of the force at the point, the force times the mode function at the point where the force is applied. All right, so, and actually we could have one of these for each basis function j. So, if we wanted to model a continuous system, let's say we had any beam, any continuous beam, and let's say we're going to use only one term in the Ritz series, so that u is just equal to psi times q. All right, so this is some elastic mode that we're interested in. All right, so if let's also suppose that psi is a mass normalized mode vector. So we've taken this from appendix, I think it's appendix C in Ginsburg. It's a known solution to the system. So if we plug that in to the equations, we'll get that M11 is just 1, and K11 is the natural frequency squared. And this will be the true natural frequency, or the exact natural frequency. So our equation of motion is just Q double dot plus the true natural frequency squared times Q is equal to capital Q, or the forcing term. Now, suppose we add a spring at a position x sub s. So we've got our beam, say it's initially free, and we put some spring at some position xs. What force will, how do we account for that? Well, one easy way to do that is to say that that spring, we will replace it with just a force, and that force will be negative the stiffness of the spring times the displacement at the point where the spring is attached. Here I'm using U as a lateral displacement. I should have used W to be consistent with what we've done in class. I'll go ahead and just fix that real quick. All right. But the same would be true if this was all axial vibration. So we can plug that in here. Our equation of motion then becomes, so the force, Qj, is minus k times psi times q. That's all the force. And this would also have to be it. So this would also have to be at the point where the force is attached. Psi of xf times q, and then we multiply by psi of xf again, and that would be, this would now be our equation. So we could rewrite this, our equation of motion, moving that to the other side, q double dot. Now notice our stiffness term has k psi of xs. Xs is the point where we've applied the spring. Probably should have just done that for both of those. Squared. Right? And so now we can, that times q is equal to 0. So now we can immediately say that our measured natural frequency squared is the true natural frequency squared plus k psi xs squared. All right? So this is very much like our simple formula that we had in the notes. One trick here, though, is what is k, right? We have to bring an Instron machine with to test the stretch, the stiffness of our bungee cords in order to use this formula. It also requires having a mass normalized mode shape, which is another thing that we might not have if we're just walking up to a structure in the lab. So to make this more practical, what we will do is, once again, we'll make an n equals 1 term Ritz series for using the bounce mode or the rigid body mode. So now what we're going to say is that W is equal to psi of some rigid body mode times Q of some rigid body mode. And if we do the same thing, and we plug in the equation of motion, and this is also a mass normalized mode vector, Q of the rigid body mode, we'll get Q double dot plus, in this case we'll get 0 for the stiffness term, because a rigid body mode by definition has 0 stiffness if we didn't support the structure. And as we had before, we're going to get a minus K of the support times psi RB of the position of the spring or the support squared times QRB. All right, and now notice this becomes the new the total stiffness term here. So we can move it to the other side, and we can say that the rigid body natural frequency squared is equal to the stiffness of the spring, support spring, times psi RB times XS squared. All right, or we can use this to eliminate K from the equation up above. It's the K is the natural frequency of the rigid body mode times the mode shape of the rigid body mode squared. So if we plug that in up above, what we get is that the measured natural frequency is the true natural frequency, both of those squared, plus the rigid body natural frequency times this ratio of the elastic mode shape and the rigid body mode shape at the point where the spring is attached. And then we square both of those. All right, so here's our easy to remember formula. And what have we learned? We've learned that the measured frequency will be the true frequency, and then it will be contaminated by this term. So the lower the bounce frequency is, the lower the error. Or if we can put the springs at the point where the elastic mode has a 0, then they won't have any effect. All right. We'd assume that the rigid body mode, usually the rigid body mode is, something that might be constant with X, right? It's just like a translation with X. There is the potential for this to blow up. Say we were trying to use this equation for this elastic, with this rigid body mode, this rotational rigid body mode. And if we tried to put our spring there, this equation blows up. We'd have to do some other kind of analysis. All right, but in that case, it basically just means we're looking at the wrong rigid body mode, that a spring in this location wouldn't do anything to this rigid body mode. We need to write the equation for a different rigid body mode. All right, so there's the derivation, and it shows you how this can be used, how a one-term Ritz series can be used to get the same equation. And we derive this easy-to-remember formula. Here we've written it with the true on the other side. And we could also write that in this format as we had before. So the big difference is that the mode shape comes into question, right? the difference between this and our easy to remember formula here is just the presence of the mode shape in that ratio. All right, let's look at some applications of this. Here they tested a free cantilever beam, or free beam. They wanted this to be a free aluminum beam, hanging it from thin bungee cords, thin strings, and looked at varying the stiffness of the supports to see what effect that would have on the error and to validate all of these equations. So they measured for different ratios of the measured mode frequency over the bounce frequency or the support frequency. They showed that the experiments agreed very well with our Ritz equation that we just derived, and showed that you could predict pretty well what the error in your natural frequency was. And in this case, they had 2%, I guess you'd say about a 2% error at this ratio of 10. So the presence of the mode shape in there threw off the equation a little bit. We were hoping to have 0.5% error at a ratio of 10. Those mode shapes gave it a ratio of 2. The damping error, actually, they calculated, well, this is just change in damping because we don't really know what we assume the true damping is what we get with the best support structure we can make. But the damping could be an error by a factor of 10 or more, right? So really have to be careful about that. And in this case, an aluminum beam that might have 0.1% damping, or 0.01% damping even, and a bungee cord that might have, 1 or 5% damping. There's a pretty big ratio there. They then went forward and applied this to a wind turbine blade. I was actually a postdoc at Sandia when this test was going on and got to see this. And so that using what they learned, they mounted the bungee cords for the wind turbine at the nodes of the first bending mode, and notice that the flat of the blade is pointing vertically. So the lowest frequency mode of a wind turbine would be this flatwise bending, or bending in the thin, bending of the thin direction of the blade. So by putting that horizontally, that mode is compared to the swinging mode of the blade on these bungee cords, and that mode has the lower frequency. The bounce up and down mode of the bungee cords would have a higher frequency. So they looked at various configurations, more loops of bungee versus less, to lower that frequency. And here we don't know what the true natural frequency of the blade is. So the best we can do is say, when we minimize everything, what's the lowest frequency that we get for the mode of interest? We can look at how that compares with the frequency of the rigid body bounce mode. And here they're looking at the edgewise mode. So in the flatwise, I think the errors were even less. But that edgewise mode went from at about 16 hertz with a bounce mode of 1 hertz, or a pretty good ratio. We see that the frequency seems to be converging. So we hope that that's the true or a very good estimate for the natural frequency of that wind turbine blade. And that was then fed to people who were modeling it and used to understand whether they'd modeled the carbon fiber and the fiberglass and the different materials within that blade accurately. All right, so that concludes our lecture for today. on support conditions. Hopefully that helps you to understand how to design support conditions, where you might place bungee cords,